The standard deviation is a measure of dispersion, and it tells you how much the data spreads around the mean. It can be understood as the average distance of the data points from the mean. And because of that, it is a very useful metric to evaluate, for example, a population, because there is always variation in the measurements of things. So how do we calculate it? For example, here we are measuring the length of some leaves of some tree in centimeters. So for example, this leaf measures 2 centimeters, this one 4, 8, 3, and again 8. So how do we calculate the spread? First, we need to calculate the mean. You know, it's the sum of all numbers over the total number of observations. So in this case, we have a mean of 5. So it will be around here. That is the average length of some leaves. And now we want to calculate how much these deviate from the mean. So one way to do it is to calculate the difference of the measurement to the mean. So this is called the difference to the mean, which is x minus the mean. And for example, in this case, we have 2 minus 5. It's minus 3. Here is minus 1, 3, minus 2, and 3. Okay? One way to do it is to just calculate the average of this, because these are the distance from the mean. So if we calculate the average, we will get the average distance from the mean. And indeed, this can be done. This is called math. Mean average distance. So if we calculate it, we get minus 3 equals 0. Wow. Why did I choose this example? Okay, it gave us 0. And it is pretty obvious because this one and this one cancel out. And then, oh yeah, these ones become 3 and it cancel out with the left one. Well, interesting, this is a problem with this approach, with the mean average distance. This was totally unintentional, but it was like, Yeah, I messed it up pretty badly yesterday, so let me try this again. Okay, so this is not math. This is actually the average deviation from the mean. And math is the absolute deviation from the mean absolute deviation. And what we do is just take the absolute value. So it's 3, 1, and 3, which give us a mean absolute deviation of, oh my god, I already forgot, 3 plus 2.4, which gives us a mean absolute deviation of 2.4. And now this is what we called math, mean absolute deviation. And this is fine, this is pretty fine. Actually, you can use it to describe a population, but the standard deviation is preferred because it adds more, it is more sensitive to extreme values, which is useful for statistical inference, as we will see. So now we are going to do the standard deviation here, but for that, let's go to last night. Perfect. So you see the problem here. It's not very convenient. So what we do is another thing. How can we get rid of the minus sign? One way to do it is to square the value. So this is the difference squared. So if we do that, we get 9, 1, alright. So this is the square difference. Now, we can calculate the average of these distances, right? So let's do that. It's 9 plus 9. It gives us 32. Just the sum. We need to calculate the average. And we just divide by the number of observations, which is over n, which is 5. So we get 32 over 5, 6.4. Now, this is something tricky because here we have our measurements in centimeters. But since we squared the distance, now this term is in centimeters squared. What does that mean? That the leaves have a variance of 6.4 cubic squared centimeters? I mean, that doesn't make any sense. So what do? It's very simple. We just take the square root of this value and get the standard deviation. So that will be the square root of 6.4 equals 2.5. 2.5 what? 2.5 centimeters. And now it makes sense because we can say that this sample of leaves have a mean of 5 and a standard deviation of 2.5 centimeters. And this goes in both directions. So it will actually be, the population ranges between 2.5 and minus 2.5 centimeters. So that's it. That is the standard deviation. Very simple, right? Oh, by the way, the sum of the squared distance is called the sum of squares. This is called the variance, and it is useful. And this is the standard deviation. Now, there's something important in here because here we divide it by the total number of observations, right? But you should never measure, by the way, you should never measure only 5 leaves. If you want to know how long are the leaves of some trees, you need to sample more. But even if you sample for 20 years, you will never sample all leaves. Or you don't have the time to measure all the leaves in a tree, so you take a sample. So this is the calculation for the standard deviation of the population. To obtain the standard deviation of your sample, instead of dividing the sum of squares by the total number of observations, you divide by, so it is the sum of squares over the degrees of freedom. And the degrees of freedom is defined as n minus 1, the total number of observations minus 1. And this is called the Bessel correction. And one way to understand this is it's like a penalty. It's like a penalty that increases your standard deviation or your variance to not underestimate the real standard deviation. I don't know if that makes sense, but this is the way to do it. Now, another useful parameter here is the coefficient of variance. It's just the standard deviation, but in proportion to the mean. So it is the standard deviation over the mean. And what? Oh, times 100 to obtain the final result in percentage. So this just tells us the proportion of the variation in regards to the mean. So for example, in this case, we have 2.5, a standard deviation of 2.5 over the mean, which is 5. We get 0.5. 0.5 times 100, it will be 50%. That's a lot. That means that the variation in our data varies up to 50%. So yeah, we have leaves that measure 8. We have others one that measure 4 too. So there is big variation here.
So in summary, if you want to know how something varies, first you need to calculate the deviations from the mean, that is, how much each observation deviates from the mean, from the average value, and then you average these deviations. However, it is not good to just average the deviations as they come out of the operation, because positive values and negative values cancel out. So one way to do it is to take the absolute values of these deviations and average them. This is good. This is actually a very robust metric, which you can use if you want, but the most widely used is the standard deviation, that gets rid of the minus values, the negative values, by squaring the distance. Then you calculate the average. Well, first you calculate the sum of squares, which is simply the sum of these values, over n, which is the number of observations, in this case 5, to get the variance. However, this term is squared, so to represent this variation in the units of the original measurements, you take the square root of the variance to get the standard deviation. Now, this is for the population. If you are taking a sample, you need to calculate the average, but instead of dividing the sum of squares by n, you divide it by the degrees of freedom, which is n minus 1.
Now, another interesting property of the standard deviation is that if your distribution is normal, then one standard deviation will contain 68% of the data. Two standard deviation will contain 95% of the data, and three standard deviation will contain 99% of the data. And this is very useful because will lead us later to statistical inference. For example, if you want to compare two populations, if one population lands here and the other one lands here, are they different? Or can you consider them as different populations, or is just random sampling of the same population, you know? But something to take into consideration as well is that if your distribution departs from normal, for example, you have a distribution that looks like this, the mean first, maybe not a very good measure, because the mean will be here and this portion of the population is not meaningful. Maybe the mode will be a better measure of central tendency, but this will be the mean and the standard deviation will be something like that. Now, this is more difficult to interpret because you say, okay, my mean is 5 and my standard deviation is 2.5 and 2.5 centimeters from the mean. So if you are given this information, you will expect that if you go to see that tree and you take the leaves, well, the majority of the leaves will be around 5, but that's not the case. You will find far more leaves that are 2.5 centimeters less than the mean, and very few leaves that are greater than an average of 5. So better here is to use the quartile interrange or something like that. Okay?